Take a look at a local file inclusion vulnerability in Gila CMS's code, use a static analyzer to find these vulnerabilities, and then take a look at a few mitigations. To start off, let's get used to the static analyzer that we'll be using. We'll be using PHP Code Sniffer with a security audit extension installed. To get started, let's run this on a simple example PHP file that has a local file inclusion vulnerability. After running it, we see we have two lines of code that are pointed out to us, line 6 and line 8. Let's take a closer look at the actual file to see if these are, in fact, true positives or false positives. Here we can see on line 6, there is an include statement that includes pages/file, and file is defined on line 2 from a GET request. This means that an attacker has access to the attack surface here and can control what is included. However, on line 8, index is included. Index is a constant string that an attacker does not have control over. This means that line 8 was a false positive. Now that we've taken a brief look at the code analyzer we'll be using, let's take a look at the attack surface for this exploit. This exploit focuses around the deletion of posts, specifically when an invalid and crafted type is used. With this invalid type, any file on the server can be included. The code for this deletion request is in cm.php. We'll open it now. Right around line 300 is the delete action function. This function handles the deletion of content of type from the registry. On line 299, the t variable is gotten from the router get function. This is our type. This type is then used to construct a gtable object, which will operate on the database. If said gtable entry can be deleted, it is deleted. If it cannot, an error is returned to the user. There aren't any obvious includes here, which means that the actual impact surface of the exploit must be somewhere else in one of the functions that is called in this code. Just from looking at the code, we can formulate a decent guess that the vulnerability is either in the router function or in the gtable function. Let's try to use our static analyzer to confirm the suspicion. I'll minimize this and pull it to the side so that we can still view our code while we run the static analyzer. Once this is ready, let's run our static analyzer on the entire Gila CMS codebase. Go ahead and point it toward var www HTML. We can see that we get a lot of output from this. In fact, if we run it through word count, we have almost 2,000 lines. This is a little too much for us to parse through. To help narrow this down a little bit, let's create a rule set that will only flag local file inclusion or remote file inclusion vulnerabilities for us. To do this, navigate to the vendor, pheromone, PHP Code Sniffer audit, and create a copy of the example base rule set that we can edit. Once you have your copy, go ahead and edit it and remove all rules except for the easy RFI line. Once that's done, we can run the code sniffer once again with our new rule set. With this, we only get about 300 lines of output, much less and much easier for us to work through. Let's go ahead and put this through a pager so we can see if the router or gtable files come up at all. As we scroll down, we should in just a moment see the gtable and router files, and we do indeed. Here we can see that gtable.php has been flagged on line 17 with a possible remote file inclusion, and router.php has a few lines of code that are all flagged as possible remote file inclusions. These 3 lines of code that have been flagged are a fantastic place to start looking for where the impact surface of this vulnerability is. Let's take a look at router.php first. The first line that's flagged is line 38. Looking at this, we can see it brings in a controller underscore file. This is defined in line 31 as source, and then a index into the controller field. This doesn't look to concern itself with our GET or type request, so we can set it aside for now. Let's also take a look at line 203 in router.php. This includes self : caching file. Once again, this doesn't seem to have anything to do with our type field, so we can ignore it for now. Let's take a look at gtable.php now. Remember that in cm.php, gtable is first called in a constructor. Our line that's been flagged is line 17. Line 17 includes the path variable. We can see in the lines above that path is defined based off the content variable that's passed in. Content is our type field. We can see here that as long as the file exists, path is defined as content. This means that if content or our type field were, say, /etc/password, line 12 would return true, meaning that path would be set to etc password, and line 17 would include etc password. This means this is our impact surface. Now that we have our attack surface, and we know where things are being included in our responses, let's consider a few mitigation approaches. The most straightforward approach would be to remove this include statement altogether. However, this would require a lot of reworking of code. Line 17 is meant to include the metadata about a given type. Without the include statement, we need to be able to include that information elsewhere, likely resulting in an entire rewrite of this code. A different approach that requires a bit less editing would be to remove lines 12 through 15. These are the lines that allow a path to be outside of a safe folder and allow it to be constructed through user's input, not through trusted input in the database. This is a much more elegant solution, however, it has one issue. We don't know where in the code base these lines are dependent upon. Simply removing these lines may appear to solve the issue, but they may break other functionality. A third solution, which is the solution that the official maintainer of this code base took, was to validate the input at the attack surface. This would result in having a few lines of code in delete action that interpreted what the T field was set to and ensured that it was set to something that made sense, was valid, and was not a local file inclusion. This requires editing very little code. However, it does leave the actual impact surface of the include statement intact, potentially allowing future vulnerabilities to continue to exist. With that in mind, there's a handful of potential mitigations in the home folder under /root/mitigation. Each of these has an approach to mitigating the attack, but not all of them will work. You can go ahead and test each one out by copying the file over into its location in the source code. For example, if I wanted to try the mitigation of cm-mit1.php, I would copy it over to its respective place in the source code. And I can also take a look at it. So this approach works by checking if a type is set to .. etc password, and if so, returns a 404 response code and exits. We can test to see if this works by running the auto exploit in the exploits folder and seeing the responses. From here we can see that this cm-mit1 mitigation does in fact prevent a local file inclusion where the files to be included is .. etc password. However, simply adding another .. in front or attempting to include a completely separate file still works. Let's now take a quick look at each of these proposed mitigations to see how it does or doesn't mitigate the issue. As we've already seen, cm-mit1 only solves a very particular version of the vulnerability and doesn't solve it in the general case. Let's look at cm-mit2 now. This mitigation stores the type field in a table variable. It then uses this variable to check with Gila's built-in types to ensure that it is a valid type that Gila already knows about. If this isn't the case, a 404 response is returned to the user, and the delete action function immediately exits. This ensures that any type that's passed in is checked and is valid. This is a very similar version of the code to what the official maintainer of Gila CMS implemented. This code does actually pass all of our tests. We can verify this by first copying it over, and then running our automatic exploit. We can see that all three local file inclusion attempts have failed. Let's copy the original version back in and take a look at the two other proposed mitigations. This proposed edit to gtable attempts to remove the ability to include files on the server. It does this by removing line 13, the if file exists, set path to content. This would work if it weren't for line 16. 16 appends content to source, meaning that all an attacker has to do is simply add an additional .. to the front. We can verify this by, as before, moving the code into the codebase and confirming the behavior. Now that we've moved it in, let's run the exploit again. And we can see that our attempts with 3 .. have failed, but an attempt with more than 3 has succeeded. Let's move the original version back in and take a look at our last proposed mitigation, router mit3. This proposed mitigation removes one of the include statements from router that PHP code sniffer flagged us on earlier. However, As we mentioned earlier, this include statement is not connected to our types or the deletion of posts. Therefore, removing this include statement won't affect how the vulnerability works. Once again, we can confirm this by moving the code into our code base and testing its behavior with our exploit. We can see that all 3 attempts have succeeded, meaning that we haven't mitigated anything in this example. As we've seen through this lab, mitigating and identifying code can be difficult. Identifying source code and using static code analyzers are both 2 important tools in identifying and mitigating code.